Hi folks, welcome to part 2 of exploring ways to hack your router. The link for part 1 you find below in the description. Enjoy the video, cheers. Okay, as you can see here, this is actually a raw dump, so the whole flash content is just dumped as it is. And these are actually things like the bootloader U-boot, Linux, rootfs. So we will have a look later in this how we can extract the data. This will be the next step, and this is quite interesting. So you can see here there's binary data, but then there's FFFF. So this is alignment to the next section which is written. So this could be U-boot now, and what's following up is maybe the kernel. Let's search for boot. And as you can see here, we find U-boot already. So this is very likely U-boot. So from the flash tool, which we can see here, I read out the flash, so that means the raw binaries, and saved it to a file which you can see here. Saved it in this folder, and you can see this is a flash dump which is 4 megabytes large. Just as a reminder, this was a 4 megabyte NOR flash, and we just have the raw dump here now in the file. Okay, what are we going to do now with this flash dump binary, raw dump binary? Let's have a quick look inside the file. And as we saw in the flash tool, we see a lot of hex values representing different contents. But what contents is this? Let's have a look and look at an explanation. So on the left side, we see the raw flash binary as I have my file. And in this particular case of this router, can also be in different routers, on other routers, we have at the very beginning the U-boot binary. So this is a raw binary containing the bootloader U-boot. And this is at a certain offset, let's say. Then it's following the kernel image with U-boot headers, which then from the U-boot is started. Then with a certain offset in the memory, we have the rootfs. In this case, it's a squashfs. Then at the end, we have a config partition, which contains all the data which should be persistent available in case of an update. And then in the very end, we have a partition called art, which contains all the calibration data. And previously, we saw all the logs while the system was booting, the Linux was booting. And as I can show you, this partition, this table showed up shortly. And here you can see the different partitions for the bootloader, kernel, rootfs, config, and the calibrations. And you can see from which start and end address these are declared. So if we go back to this image and show this in parallel, we see, okay, from 0 to 20,000 hex, we have the U-boot. Following with the kernel. So the kernel starts at offset hex 20,000, and so on and so on. Okay, let's have a look at our binary file. While on the left side this table is open, and let's have a look inside the file. So as we can see, from 0 to 20,000 hex, there's the U-boot. Let's scroll down. Maybe a little bit faster. Yeah, and here it was. You see, okay, after a certain offset, there are lines with a star. That means there are the same bit pattern for that many lines as long as it doesn't change. So here we have a change, so this is the reason why this is shown. And this means, okay, we reserve space as an offset for, let's say, U-boot, but we don't have to fill it completely. So F normally means, hey, this is the erased flash. And at 20,000, we see the kernel image starts. So let's see, the kernel image goes to 120. So you see there's a lot of information. You can also jump there with the command line parameter, but we will go through like this, that you can see, hey, this is a lot of, kernel image is quite big. As you can see, these are a lot of lines. And let's see when the FF is starting. And here we saw it. If we go back, you can see the kernel image ends with this line. But this line is far away from the final offset where this, let's say, section ends. So that means it can be declared, but for future updates, for instance, because rootfs will always start there, for instance, you still have space in case you want to update the kernel. Everything is erased and written by FF, and then maybe the kernel image goes a few lines longer. So what could we actually do? We could actually extract the file ourselves according to the offsets we found here for the different MTD petitions. Or there's also a tool called binwalk. What is binwalk actually doing? Binwalk looks inside the raw binary file for signatures to identify different types of data. Let's say U-boot or Linux or SQuashFS, or here in this case a device tree, and so on. And I would just say, let's go back to the file. Here is the file, and if we put binwalk -- help, and I would say just let's do here a signature scan inside the file and see what's showing. Okay, so what we see is actually, we see the offset from the beginning of the file and what it has found. So here it has found a U-boot string. Let's quickly cross-check this just for illustration. We will skip that many bytes and we should see also the U-boot string. And we can see it here. So the tool found the U-boot string at this offset, and this means this is that offset in the file. Good. What else does it found? Okay, it found a U-image header. A U-image actually is normally the name of the kernel image with U-boot headers. And it found here the U-boot headers with the entry point and so on. This is very important. We will come to this in a later video. And then it finds, and also there's some additional information like, okay, CPU architecture is MIPS, operating system is Linux, and compression type is LZMA. And next it found the LZMA compressed data. This is actually the actual kernel image. Then it found TP-Link firmware headers and further information about it. And at the end, with the hex 120,000 offset, if we go back to the picture, if we look for the rootfs, this is actually the beginning of the rootfs type. We find a SQuashFS file system. It's again LZMA compressed and was created here in late 2012. So let's have a look what we can do with binwalk to extract the data. And we have general options, we have extraction options, and here we have the -E, automatically extract known file types. And this is what we actually will do. binwork -e flash. Okay, so it created a new folder here, flash dump b2 extracted. Let's go in there. Let's have a look what is found. So it found a squash FS, which actually can be read by unsquash, but normally vendors like TP-Link, they have a special magic, so with the standard tool it doesn't work that easy. And then let's go to squash fs root, and voila, here we see the root file system of the target. So what were we actually doing? We were looking for the password hash, or we wanted to find out the password to log into the device. So if we go to etc and then in the shadow file, here we find a user called root, and then we find some strange numbers. And so just quick information about what this shadow file contains. Like always, you find this on my website, these information, and the link is in the description of the video. So if we look at this example, this is a string which can be within a shadow file. And we see the blue one here is actually the username, in this case root, but it can also be any other name like Peter, Teresa, or whatever. The green one is actually the algorithm type, the hash algorithm type. So one represents MD5 based password algorithm. Then we have the yellow string. This is actually the salt, which is appended to the password before the hash is generated. The purpose is to prevent people using rainbow tables. We come to this later. And the green one is the actual hash. There are additional information here at the end of the string, which are representing, hey, how many days you're allowed to have a password before you have to change it, and so on. But this is not so important for now. So in order, if you want to generate the hash out of a password with a given salt, you can use OpenSSL. For example, if you use OpenSSL passwd, passwd, -1 stands again for MD5, you give a salt and the password and you get an output which looks actually the beginning of the shadow file without all these date codes. So what is Hashcat? Hashcat is a password recovery tool, also stated here as the world's fastest password cracker. So normally every password is saved as a hash value. And Hashcat can support you with the help of GPU acceleration, here supported by AMD GPUs, but also NVIDIA GPUs. Here are the hash algorithms. There are very common ones or very known ones like MD5, SHA-265 and so on, but there are many more. So this open source software, you can give it a target hash and a word book. The word book can contain, let's say, all kind of common passwords, every word of Wikipedia, whatever. And the tool will check all the entries of the word book to find the target hash of interest you gave it at the startup. Okay, we are ready to use Hashcat. So I'm using Hashcat installed by my apt default repository. Let's quickly check what version do I use. It's version 6.2.5. And now I will figure out the resources of my PC in order to run the operations by Hashcat. And I do this with the -i command. I mean, -i means backend info, which shows information about the backend API. Okay, let's run this. And now it's getting the background information. It takes some time. All right, we are seeing results here. Let's scroll up. So here we are seeing the information, especially the OpenCL info. OpenCL stands for Open Computing Language probably some of you already know. And there are two kind of drivers available. One is the Mesa driver, which is an open source driver. And the other one is an AMD proprietary driver. And it is the same resource. We see, okay, there's a device ID 3, which is an AMD Radeon RX 6800. And there's an AMD Radeon graphics with a device ID 4, which is actually my onboard graphics card. So this is my dedicated, inserted in the PCI Express slot, and this is my onboard or on CPU or APU consisting graphic cards. Below here we have the proprietary driver. You see the same cards with maybe slightly different specification and driver information. And what I'm going to use, Hashcat, is device 5 and 6. So you can combine several devices for your calculation, and we will later see what hash rate the individual devices and the combined performance will give you. Okay, so then let's have a closer look on Hashcat on the help page again. Yeah, and let's have a look at the basic examples. So we always have a kind of attack. The attack mode is here an option -A, and here is 0. And an attack means, okay, we have the target hash and we can brute force somehow by trying randomly or according to a word list, or brute force, as I mentioned, or a combination of both. And there are some other attack vectors. You can try to find out the target hash. And if we go to attack modes, just give me a second. Attack modes, you see here is straight, which actually means dictionary or word book attack. Combination of brute force and a dictionary attack, and there are further methods available. Then we have the -M. -M is actually the hash type. Let's quickly look in there. -M is actually the hash type. And the hash type we need to find ourselves. I will do this down here, and then because the hash types, all these are the hash types, there are dozens of them. But we will just grab for Unix. And let's see. Okay, we have the category operating system and MD5 crypt, which is usual to Unix, which is original from Unix, and we will take the 500 as the hash type. Going back to the example, then we can give the actual hash, or a file which is containing the hash, which in this case is our shadow file, and we can give the dictionary. So this is now very basic. There are some more parameters I want to discuss just to use Hashcat efficiently. Okay, let's switch back to my webpage. All right, I hope you can read it. I will just zoom a little bit in. Here is the command I use for this video. As discussed, we have the -A, which is the attack mode, dictionary attack in our case. -O is in this case, and this enables an optimized kernel. So there's some kind of logic which is loaded to the graphics card, and there can be a higher performance if you limit the password. So you have limitations in the password length, but higher performance. We have the W3, which is actually the workload profile. We can have a quick look. So I'm choosing the profile 3. So I'm using the profile 3, which can lead to an unresponsive desktop, but from my experience it's still okay. You can still do things. Maybe you cannot play any games, but it's okay. Going back to the web page. Okay, then we have -s, which is actually the type of candidate being used. The -d is the backend devices to use. From the previous information Hashcat gave us, we decided to go with device 5 and 6. These are actually, if I scroll up, you can see it. These are actually the 2 graphic cards, my dedicated and my onboard or on CPU graphics card with the proprietary driver. Then we have status. That means the Hashcat will give us our status and status timer 1 second. That means that Hashcat will give us information about the progress once a second. We have the hash type, which we looked into. This is 500. This is actually the file containing the hash, which we had a look on before. And very important here, we have a dictionary or word book or password list. I downloaded this from this link. You find this on my website. You can use any other word book you find or create it yourself. So I would say let's give it a run. So let's see, where do we need to go? We need to go to etc, and here should be the shadow file. Here's the shadow file. Let's have a quick last look into the shadow file. We see again our string, which we just explained a few minutes before. And now I will copy the hashcat command from my website. Here you can see it as discussed, and let's execute it. Okay, and Hashcat starts the dictionary attack. So let's just wait a few seconds, and then we will have a detailed look on what is shown here on the statistics. Okay, so this is updated once a second as we set this in our command. This was the status and status timer 1 second. You see, okay, a session of headcap is running. It's hash mode 500, which is the MD5 crypt Unix uses. We have a target hash. This is actually the string contained in the shadow file. We used an optimized kernel, so we don't expect that the password is exceptionally long. Here's the guest base. So this is actually a over 100 gigabyte large word book. And here, this is very interesting. We use the devices with the device ID 5 and 6. So 5 is my dedicated graphics card. So here we have round about 1.8 million hashes per second. And here we have the onboard graphics card or on CPU or APU contained graphic card, which it's roughly almost 500 kilo hash, and we have a combined performance of almost 2.3 million hashes. Now here you can see the progress. So all these hashes has to be tried out. This is actually the already processed amount of hashes, and this increases with 2.3 million roughly. It will also depend on the temperature and the clock speed of the graphics card. So if it's getting too warm, then it slows down with the performance. And yes, here are some further information which are actually not of relevant for us. Okay, let's see what it is doing. So we have already 4%, and depending on if it is contained in the word book, if it's rather at the beginning, middle, or at the end, we have to wait, or we will not find it at all. So let's see. And it has found the password. So this was our target hash, as we can see here. And the status is correct. And this is actually the password, Zoho admin. So we already had almost 85% done in the word book. We were currently at these words, Säuple and whatever. And let's cross-check what the password gives with OpenSSL. So OpenSSL passwd -- help. Let's have a quick look. What I need to enter here. So -1 from MD base. So -1 minus salt, and then give the salt minus salt. And actually this is the salt. Oh, let's take it from here. So this is actually the salt. And the password Zoho admin. And if we compare this is exactly the same hash. So Hashcat found actually the password which produces together with the salt and MD5 this hash. So what we are going to do now, let's put back the flash and solder it back to the board, and then we will try out if for the user root this is the root password. Alright, back to the hardware. Here we have the router board, and here we have actually the flash chip, which needs to be soldered here. Let get me out of it. So this is actually the flash chip, and we will solder it back in order to test the password. So let me get my oscilloscope and soldering equipment available. Alright, good. I have my soldering equipment available and also my microscope, which is actually quite dirty here. Shame on me. And let me quickly prepare everything for the soldering. So let's have a look on this little thing here. All right. Okay, this is our flash and it looks quite nice. Oh my god. So this is our flash. We see even the numbering on there. And here is the board. I will put the flash safely away. And here we have the board back. And here's actually the place where it needs to go. One important matter here, we need to solder it in the right orientation. And this little knob, what we saw here on the chip, needs to be in this indicated notch. So this is how it needs to go. Alright, I have the board here. I connected the serial line serial USB adapter. And let's power it. On the left side I have the terminal where I can see all the outputs. Yeah, and let's turn on the device and see what's going on. Okay, it boots up, so nothing is damaged. Alright, let's just give it a few seconds. Okay, I have the login here, so I use the user root and Zoho admin, and there we are in. See, we can see even the shadow file. We can see the proc file system. Here we go. Oh. And okay, we are in the system. This worked. Thank you for watching and see you next time for the next video. Bye.